Good morning, sir.
Good morning, madam. Good morning, madam. Madam, whether the screen is visible, madam?
Yes, sir. Good morning to everyone. That's the thing about people who think they hate computers. What they really hate is lousy programmers. Larry Newman. Institution vision. JPR Institute of Technology aspires to provide technical education in futuristic technologies with the perspective of innovation, industrial, and social applications for the betterment of humanity. Hope everyone is safe and healthy. I am Deepika, student third year of ECE department. On behalf of JPR Institute of Technology, Department of ECE and EEE, we are glad to invite you all for the second day of this FDP event, 6 days of faculty development program on emerging advancement of wireless communication and applications of power electronics in stream grid Smart Grid System. The faculty development program it insists to provide financial assistance to facilitate upgradation of knowledge, skill, and intends to provide opportunities for induction training to teachers employed in engineering and technology. Now I welcome Dr. Kamachi Ma'am, HOD of EC Department, JPR Institute of Technology, to deliver the integral address and introduction to this. Thanks, ma'am.
Good morning, everyone. It is glad to welcome you all for the second day of this 6 day FDP program. And I would like to thank every one of you for giving the support on the first day to make it as a successful. And I would like to welcome you on behalf of the management, all the faculties of various institutions, the resource person, Dr. R. Sandil Kumar sir, Assistant Professor of EC Department, Government College of Engineering, Erode, in delivering a topic in analog and digital communication using open software, simulation software. Uh, I would like to welcome all the participants of the program. I'll hand over the session to Deepika.
Okay, shall I start, madam? Madam, shall I start, madam?
Yes, sir. Sir, yes, sir. You can start with your presentations.
Yes, madam. Madam, whether the PPT is visible, madam? Madam, whether the PPT is clearly visible? Presentation. Nancy, madam, whether the PPT is clearly visible? Hello?
Well, sir.
Madam, whether the PPT is clearly visible, madam?
Yes, sir.
Are you able to read the content, madam?
Yes, sir. Yes, sir.
The second slide,
Yes, sir. Visible one, sir.
the equations are readable.
Yes, sir.
Okay, right. Okay. Thank you, madam.
Thank you, sir.
Good morning, everyone. Welcome to the FDB on advancement of wireless communication and applications of power electronics in smart grid system. Uh, Organized by Department of EC and EEE JPR Institute of Technology. In the second day of FDB, I am going to discuss about the how to code Scilab and Python. These two are open source softwares. Using this software, how to code analog and digital communication algorithms and equations. Okay, here I'm going to give some demonstration of some of the analog and digital communication experiments using the open source software Scilab and Python. Most of you are using Python, and few are using Scilab. Both you can use Scilab and Python for simulating analog and digital communication experiments. Scilab is most suitable for analog and digital communication system. So many users are they have developed so many atoms and toolboxes related to analog and digital communication using Scilab. Python, you have to write your own code in Python. You don't have any separate toolbox for analog and digital communication in Python. Whereas in Scilab, you have so many toolboxes available related to the analog communication simulation and digital communication simulation, and also for wireless communication also. Okay. Uh, First, let us start with analog communication. In analog communication, I am going to discuss three basic modulation techniques: AM modulation, FM modulation, and PM modulation. Um, for AM modulation and FM modulation and PM modulation, I'm going to I'm going to simulate these three experiments, and I'm going to show you the output. So, without knowing the equations, we are not able to write our own code. Here, I haven't used any built-in functions available in Scilab. Here, I have written my own code. I am using for, while, if loop only. I'm not using any built-in functions available in Scilab. So I'm directly writing the. I have written the Scilab code directly from the mathematical expressions given in this slide. First one, we are going to see the AM modulation. What's the expression for the carrier wave? Vc of t is equal to Ec sine 2 pi fct. And what is the equation for AM modulated wave? VAM of t equal to Ec plus Em sine 2 pi fmt sine 2 pi fct. What is Em sine 2 pi fmt? This is nothing but your modulating signal. This one is the modulated signal, AM modulated signal. What do you mean by AM modulation? The amplitude of the carrier varies with respect to the modulating signal. Instead of EC, what you are getting in the AM modulated wave, EC plus EM sine 2 pi f of t. So this one is the AM modulated wave. And all those equations and the diagrams related to the analog modulation are taken from the Advanced Electronic Communication System by Tomasi. And all the figures and equations related to the digital communication are taken from the digital communication by Simon Akenbo. So you can refer analog communication using Tomasi, and you can refer digital communication. Go for Simon Aken. Prokias also is a very good book for digital communication. Type okay. What is the second slide? So this one is the VC of t is the carrier's expression, mathematical expression for the carrier signal, and the VAM of t is nothing but the mathematical expression for the AM modulated wave. On what is second slide? I am feeding these inputs: EM equal to 8 volts, EC equal to 10 volts, FM equal to 2 hertz, FC is equal to 10 hertz, sampling frequency is equal to 1000 hertz, FS is equal to 1000 hertz. Okay. Um, this one is a simulated output. This one, the topmost is the waveform for the modulating signal, blue color, and the second one is the carrier signal, and the third one is the amplitude modulated signal. This one is the simulated output. Okay. Now I am going to the Scilab software. Okay. All those programs are shared to the your professor Nancy Madam. All those are available in the Google Drive. The drive link shared to the Nancy madam. You can get it from the Nancy madam. PowerPoint presentation, Scilab programs, and Python programs. Madam, whether the Scilab editor is visible to you, madam? Madam, Nancy madam,
Yes, sir.
whether the Scilab editor is visible to you, madam?
Yes, sir. Yes, sir.
Are you able to read what is EM, what is CC, what is FM in this editor?
Yes, sir. EM equal to 8, EC equal to 10, FM equal to
Okay,
2, sir.
okay, madam. Okay, madam. Here I am not using any built-in functions from the Scilab. Here I have written the um, directly I have coded the mathematical expression. What is the expression for the modulating signal? Vm is equal to its amplitude Em into sine 2 pi fmt. So this one is the modulating signal, and second one is the Vc is equal to Ec into sine 2 pi fct. This one is the expression for the carrier signal, and x is equal to Ec plus Em sine 2 pi fmt sine 2 pi fct. Okay, so this one is the expression from the AM modulated wave. AM modulated wave. Okay, subplot 3 comma 1 comma 1. So I want to plot all these three. First one modulating signal, second one carrier signal, third one AM modulated wave. Subplot 3 comma 1 comma 1. That is three rows. In the plot, I am going to create three rows. In the um, first row, first column, I am going to plot modulating signal. In the second row, first column, I am going to plot the carrier signal. In the third row, first column, I am going to plot the amplitude modulated signal. Go to execute, file with no echo. Yeah. So the first one is modulating signal. F is equal to 2 hertz. That's why I'm getting 2 cycles for modulating signal. The carrier signal frequency is 10 hertz. That's why we're getting 10 cycles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this one is the A modulated signal. Since I have chosen the ratio EM delta EC, amplitude of the modulating signal divided by the amplitude of the carrier signal ratio less than 1, I am getting undermodulated AM wave. If I have chosen EM by EC is equal to 1, I can get critically modulated signal. If I am choosing EM by EC greater than 1, I am going to get over modulated signal. Okay. Nancy madam, are you able to see this graphic window?
Yes, sir. It's visible, sir.
Okay. And what is the second figure? This one has the demodulated wave. AM demodulated wave. So approximately I am getting modulating signal here. Envelope of the modulating signal here. AM demodulated waveform. AM demodulated waveform. So what is the frequency of the modulating signal? 2 hertz. So AM demodulated output should contain two cycles. This one is the first cycle and this one is the second cycle. So I am getting 2 hertz here. Okay. I am getting the envelope of the modulate, modulated signal here. So this one is nothing but your modulating signal. So what is the frequency of the modulating signal given to the AM modulator input? 2 hertz. 2 hertz in the sense 2 cycles. So in AM demodulator output, I should get two cycles only. I am getting two cycles here. Okay. So what is the program for the AM demodulator? Go below. The same program used for AM modulator and AM demodulator. Here I have written a function for AM demodulator. What is the input given to the AM demodulator function? X, AM modulator wave, BC, carrier signal amplitude, FC, carrier signal frequency, FS, used to sample those analog signal, EM, modulating signal voltage level, EC, carrier signal voltage level. So what I am doing here, just multiplying the modulator signal with the carrier signal, I'm just going to filter out this multiplied signal by using an low pass IER filter using the command filter. Okay, and I'm getting AM modulator signal here. So multiply AM modulator with the carrier signal and filter out using the IER low pass Butterworth filter. You can get the AM demodulator output. AM demodulator output. So this one is the function from this point to this point. AM demodulation. This point to function for AM demodulator up to this one. I'm going to call this function AMP demod. Okay, then only this function will work. Okay, okay. If you want to run this function, you have to call this function AM demod by giving these inputs X, BC, FC, FS, EM, EC. Madam, shall we go to the second experiment, madam? Madam,
Yes, sir.
any doubt in this first experiment?
No, sir.
Okay. This one is the log diagram of AM demodulator. This one is available in the all the textbook. AM demodulator output. Okay. The second experiment is FM demodulator. Okay, this one is also referred from the Advanced Electronic Communication System by Thomas book. Okay, you can refer any book, but you have to write the code according to the equations given in that book. Okay, so mostly equations are same in all the books. Okay, that was for FM modulator. So what is the expression for the FM modulator output? Dc into cos omega ct plus k1 v1 divided by omega m sin omega m t. So what is FM modulation? The frequency of the carrier signal. What is the frequency of the carrier signal? Omega c varies in accordance with the modulating signal. Okay, then only we can get FM modulation. Okay. So what is the difference between FM modulation and PM modulation? FM and PM modulation, you are getting difference here. If you integrate the this expression, right, you will get PM. And otherwise, if you differentiate PM, you will get FM, right? Okay. So how you can get FM? By changing the carrier frequency according to the modulating signal. This one is the modulating signal. According to the modulating signal, you will get FM modulation. You will get FM modulation. Okay. So this is the simulated output. The top one is the modulating signal with the FC is equal to FM is equal to 5 hertz. So for 5 hertz, you should get 5 cycles 1, 2, 3, 4, 5, and the carrier signal 10 hertz 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and FS is equal to 100 hertz. So this one is the third figure is the frequency modulated signal. Frequency modulated signal. Here you can clearly identify the difference in the change in frequency there, right? So up to this, you are getting some frequency, and from this point to this point, you will get some different frequencies. Okay, go to program number 2, FM modulator and demodulator. So here EM equal to 2. Okay, EM equal to 2 and EC is equal to 6, FM equal to 5, same value. Okay. So what is the expression for the modulating signal? VM equal to, what is the expression for the modulating signal? VM equal to EM sin 2 pi FMT. And what is the expression for the carrier signal? DC sin 2 pi FCT. And this was in the frequency sensitivity. And this one is the expression for the FM modulated output. FM modulated output. FM modulated output. So here I am going to again divide the plot into 3 rows. First row, first column, I am going to plot the modulating signal. Second row, first column, I am going to plot the carrier signal. Third row, first column, I am going to plot the FM modulated output. And below that, I have written the function for FM demodulation. X is the FM modulated input, carrier signal, modulating signal amplitude, carrier signal frequency, sampling frequency. The discriminator operation is performed by this command. X diff is equal to difference of x. Okay. These two lines um, perform the hardware part of discriminator, FM discriminator. Okay. And then again, this multiplying this with the carrier signal by using a filter, again filter out this discriminator output. Okay. Okay. Filter with the filter coefficients, you will get what FM demodulator system. So first we are going to okay. Topmost is the modulating signal with the FM is equal to 5 hertz, carrier signal with the frequency 10 hertz, and third one is the frequency modulated signal. If you want to what uh, show more frequency changes in the frequency modulated signal, you have to increase the modulating signal frequency. You have to increase the modulating signal frequency because carrier signal frequency varies according to the modulating signal. So you can change the modulating signal amplitude and frequency, you will get more changes in the frequency modulated output. Madam, are you able to visible this graphic window, madam?
Yes, sir, it's visible, sir.
Okay. And the second one is the FM demodulator output. This one is the FM demodulator output. Approximately recovered the modulating signal. Not exactly. Approximately recovered the modulating signal envelope here. So what is the frequency of the modulating signal? 5 hertz. So FM demodulator output, you should get 5 hertz. Okay. 5 hertz in the sense 5 cycles. Check whether you are getting 5 cycles. This one is 1, 2, 3, 4. So what is the first cycle? This one is the first cycle. This one is second, 3, 4, 5. Approximately recovered the modulating signal envelope at the FM demodulator output. Okay. So what is this this filter, sir? IAR. Madam, are you able to read this one? H is equal to IAR 5, LP, but SC by FS 0. Are you able to read this, madam?
Yes, sir. It's
Okay,
visible,
what
sir.
is this? So this one is the uh, low pass IAR filter. Low pass IAR filter. So why you are using low pass filter? What is this low pass filter? This low pass filter is nothing but your reconstruction filter. நீங்க இந்த பிளாக் டயராம்ல சைமன் ஆக்கன் புக்ல ப்ரோட்காஸ்ட் புக்லாம் பார்க்கும்போது இல்ல எலக்ட்ரானிக் கம்யூனிகேஷன் சிஸ்டம் பை கென்னடி இல்ல டொமசி எந்த புக் ரெஃபர் பண்ணாலும் டிமாடுலேட்டர் அவுட்புட்ல வந்து ரீகன்ஸ்ட்ரக்ஷன் ஃபில்டர்னு போட்டுருப்பாங்க. வாட் யூ மீன் பை தட் ரீகன்ஸ்ட்ரக்ஷன் ஃபில்டர்? தட் ரீகன்ஸ்ட்ரக்ஷன் ஃபில்டர் இஸ் நத்திங் பட் யுவர் லோ பாஸ் ஃபில்டர். ஓகே, நீங்க ஹார்ட்வேர்ல லோ பாஸ் ஃபில்டர் வந்து வேற மாதிரி டிசைன் பண்ணுவீங்க. ஒன்று ஆகாம் யூஸ் பண்ணுவீங்க, இல்லை வேற ஏதாச்சும் டிவைசஸ் யூஸ் பண்ணி இண்டக்டர் கெப்பாசிட்டிலாம் யூஸ் பண்ணி லோ பாஸ் ஃபில்டர் டிசைன் பண்ணுவீங்க. In software simulation, I am here using IER filter, low pass filter. IER low pass filter. This low pass filter is nothing but your reconstruction filter used at the demodulator output. Demodulator output. Okay. So what is this 5? Filter order 5. Why I am using 5 here? Because I am using what modulated signal frequency is equal to 5 hertz. So proportionally I am using is 5, filter order equal to 5. Okay, what is LP? Low pass, BUT Butterworth filter. So how you feel this filter cutoff frequency? FC divided by FS. Normalized cutoff frequency FC divided by FS. And then is the FM demodulation block diagram. So the section one is the your discriminator. Okay, FM discriminator, FM demodulator output, simulator output. Then PM. If you integrate that what? If you integrate PM, you will get FM. If you differentiate FM, you will get PM. So that is the relation between FM and PM. So instead of sine omega mt, here in PM you are getting cos omega mt. So this equation is also referred from the advanced electronic communication system at Tomasi. Okay. So what is PM input? Modulating signal, carrier signal. You are getting the phase modulator output here. Here you can clearly visible phase changes here. Okay, input EM equal to 2 volts, DC equal to 6 volts, FM equal to 5 hertz, FC equal to 10 hertz, sampling frequency is equal to 100 hertz. Okay, and this one is the next one is the PM demodulator signal output. So how many number of cycles you are getting at the PM demodulator output? 1, 2, 3, 4. 4 clear cycles and one is uncleared. So you are getting 5 cycles at the PM demodulator output. That means the modulating signal frequency is equal to 5 hertz. Go to the third program. Open. You can use this icon. PM demodulation. Okay, FM equal to 5 hertz. You can use FM equal to 5 hertz. These are green color are command lines. Okay, green color are command lines. This one is the modulating signal. This one is the modulating signal. This one is the carrier signal. And S is equal to EC sin 2 pi FCT, K into EM sin 2 pi FMT. PM modulated output. And whether the Scilab code corresponding to the equation is correct or not, madam? Nancy, madam? EC sin 2 pi FCT or omega CT plus K into modulating signal EM sin 2 pi FMT. Madam, are you able to read this equation, madam? PM modulator output.
Yes, sir.
Okay, madam. So similar to AM FM, and there I have divided the plot into 3: one for modulating signal, one for carrier signal, one for the phase modulated signal, and I have written the function for PM demodulation. Okay, more or less similar to the FM demodulation. And here I call the PM demodulation function by writing the separate command PM demod x comma vc em ec fc fs. So we are going to simulate this one file with no echo. Either you can use SCE or you can use SCI for Scilab programs. MATLAB programs are saved with the extension .m, C saved with the extension .c .cpp, Java, right? So similar to this, Python.py. If it is IPython network .ipy, similar to those softwares. If you have written the code in the Scilab, you can save it with the .sce extension or .sci extension. Okay, yes. So the topmost one is the modulating signal, and second one is the carrier signal, and the last one is the phase modulated signal. And the figure 2 shows graphic window of the reconstructed original signal or approximate original signal. Approximation of original modulating signal. Modulating signal frequency equal to 5 Hz. Here I am getting 5 Hz at the PM demodulator output. One first cycle, second cycle, third cycle, fourth cycle, fifth cycle. Okay. Madam, shall we go to fourth experiment, madam? Madam,
Yes, sir.
shall we go to fourth experiment? Digital modulation techniques.
Yes, sir.
Okay. Um, so in digital modulation techniques, here we are going to discuss ASK, FSK, PSK. What is ASK? Madam, are you able to read this equation, madam? Are you able to read this equation? AC,
Yes, sir.
AC sin 2 pi FCT for data equal to 1. If data equal to 0, 0. For FSK, if data equal to 1, you are giving some other carrier signal AC sin 2 pi F1T. If data equal to 0, you are sending some other carrier signal AC time AC sin 2 pi F2T. And for PSK, if data equal to 1, it is transmitted without any phase shift. If data equal to 0, it is transmitted with 180 degree phase shift for BPSK. For BPSK. Madam, are you able to read this equation, madam?
Yes, sir.
Yeah, okay, okay. Okay. This one is the simulated output of um, um, ASK. So this one is the carrier signal, analog carrier signal for digital modulation. This one is the ASK modulator output. What is the digital binary data given to the ASK modulator? 1, comma 0, comma 1, comma 0, comma 1, comma 0, comma 1, comma 0 is 8-bit data. First, for 1, you are getting carrier signal at the ASK modulator output. For 0, you don't get any output. And again, for 1, you are getting some carrier signal output. For 0, ASK output not transmitting any signal. Okay. So 1, 0, 1, 0, 1, 0, 1, 0. For AP data, okay. This AP data, for this carrier signal, you are getting this output, ASK modulator output. And this one is the FSK modulator output. For binary 1 is transmitted with a carrier signal of frequency 2 Hz. Binary 0, binary 1 is transmitted with a carrier signal of frequency 4 Hz. Binary 0 transmitted with a carrier signal of 2 Hz. Okay. So the first one is binary 1, and this one is binary 1. Okay. transmitted with transmitted with the carrier signal frequency of 4 hertz, and second one is the binary 0 transmitted with the carrier frequency of 2 hertz. So 1 0 1 0 1 0 1 0. Same data used for FSK modulation and PSK also. For binary 0, the carrier signal transmitted with the 0 phase shift. For binary 0, for binary 1, the carrier signal transmitted with 0 phase shift. For binary 0, the carrier signal transmitted with 0 phase shift. Sorry, 180 degree phase shift. Here you can note down the phase shift, 180 degree phase shift here. This one is the binary 1 transmitted with 0 phase shift. Binary 0 transmitted with 180 degree phase shift. Right? 180 degree phase shift. So this one is the output of BPSK, binary PSK modulator output. So for giving input, go to console window. This one is the Scilab console window. Madam, are you able to view the Scilab console window, madam?
Yes, sir, it's visible, sir.
Frequency equal to 2 hertz. The data given in the example 101, comma 0, 1, comma 0, 1, comma 0, 1, comma 0. Right? So this one is the carrier signal 2 hertz given to the ASK modulator, FSK, PSK. This one is the ASK modulator output. Madam, blue color இருக்கிறனால தெரியுதா?
தெரியுது சார், எல்லா ப்ளூ லைன்ஸும் தெரியுது சார், விசிபிளா இருக்கு.
Okay, okay. And then this one is the FSK modulator output. And third one is the BPSK modulator output. BPSK modulator output. Give clear to clear the variable content. You can clear the console window by using the command CLC. Okay. Next one is Hamming encoding. Hamming encoding. Here the program is written for Hamming encoding 7,4. Example. What is 7? Code word length equal to 7. Message word length equal to 4. Parity bits equal to 3. So how we are going to generate the parity bits for Hamming encoding H7,4. The MSB of parity bit is generated by XORing. First XOR M3 with M1. What is M0, M1, M2, and M3 are message bits. Message word length equal to 4. In this, M3 is the MSB and M0 is the LSB. Similarly, in parity bits, B2 is the MSB and B0 is the LSB. How to generate B2 from message words? Message word. First XOR M3 with M1 and then again SR the result with M0. For M1, for B1 also. For B0, this expression. Okay. So, what is the value of M3, you have to give the all the MSB for 16 different message words, and second bit of message word, and third bit of message word, and the fourth bit of message word. Okay, for 15, what is the corresponding message word? 1110. The parity bit is equal to 010. The code word generated equal to 010. First, upon parity bits first 010, followed by message word 1110. For message word 2, what is the corresponding binary digits? 0001. Corresponding parity bits 101. The generated code word equal to first append parity bits 101, 101, followed by the message word 0001. Go to having encoding. Okay. So I have tested the results for all the programs. You can refer the program, how to feed the input. You can refer the program itself. Okay. Here I have tested the example input given to the program. For first message word, go to console window. Test this. What is the second bit of message word? This one. Copy this one from the editor window of Scilab and paste it in the console window. The third bit of message word. Enter the third bit of message word. Right? Okay. What is the 16th message word? 111. Corresponding parity bits 111. Code word equal to first append the parity bits 111 followed by the message word 1111. Starting from message word 10002 ending with message word 16 1111. Madam, madam, whether participants have any
Yes, sir.
doubt up to this, madam?
Okay, sir.
Uh,
Will ask.
okay, madam. Share them the Google Drive link, madam. So everyone can access
Yeah,
that Google
okay,
Drive
sir.
link. They can download Scilab programs and Python programs.
Okay, sir.
For
Okay.
Scilab, so they can run those Scilab programs. If they have any doubt, they can ask. And
Okay, sir. I will
also
share
Python.
my sir.
Okay, ma'am. Okay, ma'am. And this one is the pseudo. Next one is the pseudo random noise sequence. Pseudo random noise sequence. This figure is taken from the digital communication by Simon Aken maximum length sequence generator. It will generate pseudo random noise sequence of period n equal to 7. Okay, what is the importance of pseudo random noise sequence? This one is particularly useful in the wireless communication for security purpose, spectrum communication technique, and also in wireless communication for security purpose. Pseudo random noise sequence. The figure shown in here is a maximum length sequence generator. It will generate a pseudo random noise sequence of period n equal to 7. What may be period n equal to 7? For every 7 values it will repeat again, once again, same values. Okay. Here, how we are going to generate periodic sequence here? For a periodic sequence n equal to 7, how many bits you need? 3 bits are sufficient. By using 3 bits, you can generate 0000 to 111 sequences, 8 sequences by using 3 bits. For periodic sequence n equal to 7, you can generate, you need 3 bits only. X3, X2, X1. So in this figure, what is X3? X3 is derived from X2. What is X2? X2 is derived from X1 after one delay from the flip flop. What is X1? X1 is the, what is modulo 2 adder is nothing but XOR. How we are getting X1? How we are getting X1? By XORing the X3 with the previous X1 value, we can get present X1 value. Okay. Period of the signal n. This one is the pseudo random sequence. In the step 1, you are getting 100, and step 2, you are getting 111. In step 3, you will get 111. Step 4, 011. Step 5, 101. Step 6, 010. And step 7, 001. What is step 8? Step 8, step 9, step 10, step 11. For step 8, again you are going to repeat this sequence 100. Step 9, 110. Step 10, 111. Step 11, 011. Step 12, 101. Step 13, 010. Step 14, 000. So for every 7 steps, the sequence will repeat. The sequence will repeat. Period of the signal equals 7 in the sense that is the actual meaning of this one. Okay, here we are going to simulate this one. PN sequence generation. Okay, initializing the value of x naught equal to 1, x1 equal to 0, x2 equal to 0, x3 equal to 0. Okay, go to control window, give you the period of the signal equal to 7, simulate this. Check whether you are getting this value. Otherwise, your program is wrong. 100, and the last sequence is 0001. Okay, so this sequence is going to repeat and repeat, repeat and repeat for every 7 values. For every 7 values. Signal space diagram for coherent PBS system. So the next program, we are going to simulate. We are going to plot signal space diagram for binary PPSK system. Binary PPSK. So, what is a binary PPSK? You have a uh, for binary 1 you are getting 0 phase shift. For binary 0 you are getting 180-degree phase shift. So 2 bits are represented in the signal space. So what is the amplitude of the first bit? Square root of EB. What is EB? EB is the energy of the bit. What is the position of the second bit? Minus square root of EB. Minus square root of EB. That is shown in this figure. Message point 1. That is binary 1 is represented here. Square root of EB. Binary 0 is represented here. Minus square root of EB. Binary 1 and binary 0 separated by 180-degree phase shift. Separated by 180-degree phase shift in signal space diagram. This one is a simulated output. Message point 1. Binary 1 is denoted by the round symbol. Message point 2. Binary 0 is represented by this mark. Rhombus mark. constellation diagram for BPSK, binary phased keying technique. Go to program. There is binary BPSK, constellation sequence space diagram, BPSK. This one is right. Binary BPSK system. Okay. In order to convert decimal value to binary, use this command DCE to binary. DCE to binary. Okay. So these are the graphical commands to position the binary 0 and binary 1. Okay. Binary 0 and binary 1. This was the X label, in phase, Y label, quadrature phase, title constellation for BPSK, legend. First asterisk shows the binary 1 message point 1, legend 2 message point 2, binary 0, 5 presents the color. Run this program. This was the constellation diagram for okay in phase quadrature phase. So this one is the message point 1 and this one is the message point 2. Again run this program. File with no echo. Yes. Okay. This one is the legend. Message point 1 uh, shown in the round mark and message point 2 in the rhombus mark. Okay. Binary 0. This one is the binary 0 and this one is the binary 1 separated by 180-degree phase. மேடம் வாய்ஸ் கீழே இறங்குற மாதிரி இருக்கா இல்ல வாய்ஸ் கரெக்டா கிளியரா கேட்குற மாதிரி இருக்கா மேடம் உங்களுக்கு?
So it is clear only, sir.
வாய்ஸ் கிளியரா இருக்கு.
Yes, sir. Yes.
ரைட் ஓகே. இந்த ஃபிகர் பேக்ரவுண்ட் வந்து கிரே கலர்ல இருக்கு. இதுல அந்த மார்க்கிங் கிளியரா தெரியுதா மேடம்? மெசேஜ் பாயிண்ட் 1 பைனரி 1 பைனரி 0.
Yes, sir. It is clear, sir.
ஓகே ரைட். கிரே கலர்ல இருக்கு பேக்ரவுண்ட் இருந்தாலும் அது தெரியுது இல்லீங்களா? பைனரி 1 பைனரி 0 தெரியுது.
Yes, sir.
ரைட் ஓகே. Okay, and then next program, signal space diagram for PPSK system. So what is a quadrature phase keying technique? Quadrature phase keying technique are represented by how many bits we are going to use in PPSK? Bits in the sense 2 bits, combination of 2 bits. So if you combine 2 bits, how many possible combinations you will get? 4. 0 0 0 1 1 0 1 1. Okay, so if you are using 2 bits to represent a signal, how many possible combinations, how many signals you can represent? 4 signals. For 0 0 you can represent 1 signal, for 1 0 you can represent another signal, for 0 1 you can represent another signal, for 1 1 you can represent some other 4th signal. Okay, in QPSK system, the debit 10 is represented with the phase shift 45 degree. The message points coordinates are plus square root of e by 2 minus square root of e by 2. Debit 0 0, debit combination of 2 bits 0 0 is represented with 135 degree 3 by 4. Message point coordinates are minus square root of e by 2 minus square root of e by 2. That is the first one. 1 0 is represented the one is positive, another one is negative. 4th quadrant. This one is the 4th quadrant, I think. 1 0 is represented the 4th quadrant. Okay. X label, X is positive, Y is negative. So this one must be represented in the fourth quadrant. 0, 0, both are negative. X and Y both are negative. So this one must be represented in the third coordinate. 0, 1 represented with 5 by 4, 5 by 4 phase shift. This one is in the second quadrant. X is negative, Y is positive. And 1, 1 with the phase shift 7, 5 by 4 represented in the X is both X and Y both are positive. So it must be represented in the first coordinate. First coordinate. Go and check in the second figure. Okay, so 1, 1 in the first coordinate, 0, 1 in the second coordinate, and 0, 0 in the third coordinate, and 1, 0 in the first coordinate. Okay, so this one is a synchronous space diagram of PPSK. 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 This must be simulated output. Constellation diagram of PPSK system. Check whether I have written the correct program. Okay. Um, XXX 10 must be in the fourth quadrant. Okay. 00 must be in the third quadrant. This rhombus mark there. Dark rhombus mark. And empty white rhombus mark on the debit 0 1. And 1 1 in the first quadrant. 1 1 in the first quadrant. Go to the program. Open. PP is the constellation diagram. And okay, execute this program. File with no echo. The phase shift is the phase shift of for different debits are generated here. Okay, if I equal to 1, you will get 5 by 4. If I equal to 2, you will get 3 by 4. If I equal to 3, you will get 6 5 by 4, 5 by 5 5 by 4. If I is equal to 4, you will get 7 5 by 4 phase shift. Okay, the phase shift for different debits are generated here. Okay, execute file with no echo. Yes. Okay. Again, go to this program. Execute. Yes. Okay. Here you are not able to see the debit 1 1. So go to this program, execute this one, place the legend properly. Okay, keep legend here. Open this. Okay. Okay, constellation diagram of PPSK system. Okay. And the next one is the direct sequence spectrum technique. Direct sequence spectrum technique, direct sequence spectrum coherent BPSK system. So this one is the block diagram of DSS BPSK, direct sequence spectrum binary specific spectrum modulation technique. The input data sequence is given, that is denoted by V of t. A pseudo randomized sequence is generated, it is denoted by C of t. By using V of t and C of t, you can generate, if you are going to generate a message word, security message word M of t. Okay, the M of t is equal to binary PSK modulator, carrier is given. Using this carrier and M of t, you are going to generate a DSS BPSK spectrum modulated output. The data B of t given to this case, example data given is 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1. The carrier used here is 2 sin 2 pi of t. Okay. This one is referred from Simon Akin book. You can go through that book. What is the output of M of t? M of t equal to this one. M of t is this one. How you can get M of t? How you got M of t here? By multiplying the data sequence with the pseudo random noise sequence, you can get M of t. Okay, this one is M of t. It's a bipolar output. Okay, bipolar output, and this one is the carrier signal. By using this carrier signal and M of t, the BPSK output modulator generate a phase keying modulator output. Uh, Here actually you are getting this signal, carrier signal, multiplying this one minus one, you will get this signal. For here you are getting some 180-degree phase shift here, 180-degree phase shift here, and then again here you are getting 180-degree phase shift. Check here, right? Okay, we are going to generate these three waveforms for DSSK, BPSK system technique. So this one is the data. Okay, this one is the pseudo random noise sequence of a period length, period n equal to 3, sorry, n equal to 7. By multiplying B of t and C of t, you are going to get M of t. Check whether these three figures are correct. The data is this one. Okay, the data is this one. B of t is this one, and the spreading code, pseudo random noise sequence code is this one. Okay, multiply this to B of t and M of t, you will get the product signal M of t message word. Then this message word is given to the BPSK modulator. Okay, this one is the carrier signal. You are getting the spectrum modulator output here. Okay, go to the program, check whether we are going to get this value or not. This figure, those figures are not. Where is the program spectrum DS spectrum? Okay, okay. This one is B of t, binary data, binary data. This one is the pseudo PN sequence, PN sequence in binary format. Madam, type பண்றதெல்லாம் பார்க்க முடியுதா madam? Are you able to view madam?
Yes, sir.
Okay. And PN sequence in polar format. It is a binary 0 is represented by -1, binary 1 is represented as it is polar format. So this one is what is M of t. This one is the message word. Okay. This one is the carrier signal. Carrier signal. Okay. First initialize the BPSK output empty matrix. Empty matrix. Then you are going to add those signals. You will get BSS, BPSK output. Okay. Select this. Okay. What is first graphic window shows? It shows data, binary data given. First 7 are binary ones. Next 7 values are binary zeros. Binary zeros are represented by -1. Then a pseudo random noise sequence. This one C of t. Multiplying these two, you will get product message signal M of t message word. Close this figure window, and this one figure 2. Message word given to the BPSK modulator, carrier signal given to the BPSK modulator. This one is the Dara sequence respector modulator output. Okay. Okay. Madam, up to this, any doubt, madam, from the participant side, madam? I am not able to the that window, command window. Any participants have asked any doubt, madam? First, they are able to check whether they are able to download those programs and PPT.
No doubt, sir.
Okay, madam. Okay. And then the next one is the differential basic key modulation, modulation, DPSK. So this one is taken from the Simon Akin book. Okay. So in DPSK, this one is the DPSK transmitter block diagram. A logic network. Using this logic network, we are going to generate. I'm going to generate the present input by using amplitude level shifter. I'm going to shift this amplitude to either 0 or some 3.14 some radians. Then by using product modulator, multiplying this carrier signal, I can get the differential phase shift keying modulator signal output here. So what is the mathematical expression for decay? Decay is equal to decay previous value, okay, multiplied with decay, that is the AND multiplication, plus this plus is nothing but modulo 2 addition, and then dk minus 1 not of inverted dk minus 1 multiplied with the inverted bk. So this logic network performs this mathematical operation. What the mathematical operation? Previous value of dk and present value of bk modulo 2 addition xr with dk previous value inverted previous value with inverted present input bk, right? Here the BK is given. This one is the example input BK 100 10011. BK inverted BK 1 is converted to 0, 0 is converted to 1, and DK minus 1 initialize with the first one value. So what is DK minus 1? DK minus 1 you are getting this one D1 110 111 this one. What is DK minus 1 inverted value? 001 Okay, multiplying DK and DK minus 1, you will get DK and DK minus 1. You will get this value. Multiplying DK naught and DK minus 1 naught, you will get this value. So what is differentially encoded sequence DK? XORing these two. 1 XOR with 0, 1, 0 XOR with previous value. Differentially encoded sequence plus initial is 1. 1 XOR with 0, 1, 0 XOR with 0, 0, 0 XOR with 1, 1, 1 XOR with 0, 1, 0 XOR with 0, 0, 0 XOR with 1, 1, 1 XOR with 0, 1, 1 XOR with 0, 1. This one is the initial value. Okay. What is the transmitted phase? Corresponding phase. 0 transmitted with phase 0, sorry, 1 is transmitted with phase 0 radians, 0 is transmitted with phase 5 radians. 5 radians. Okay. So in DPSK, 1 is transmitted with phase 0 radians, 0 transmitted with the phase 5 radians. 5 radians. This one is a simulator output. BK equal to this one, same value. BK not this value. Differentially encoded sequence equal to this value. Transmitted phase in radians. 1 is transmitted with the 0 radians. 0 is transmitted with the 5 radians. Okay. Now we are going to simulate DPSK. Open DPSK. Execute this program. Here. execute this program. File with no echo. Okay, right. So this one is the output of DPSK modulator. DK not differentially encoded sequence. Okay, the transmit corresponding transmitter phase in radians. For one transmitted to 0 radians, 0 transmitted to 5 radians, 3.1415. Pulse code modulation transmitter. What are the blocks available in the pulse code modulator transmitter input transmitter? Um, a given signal band limited by using a low pass filter, then discretized converted into discrete samples using sampler. The sampler output quantized by using a quantizer. The quantizer output is converted to binary values by using an encoder, then transmitter. So these are the basic building blocks available in the PCM transmitter. The low pass filter is to limit the input signal frequency, band limited signal. So we generate a band limited signal. That band limited continuous time signal converted to the discrete time signal by using a sampler. The discrete time signal quantized by using a quantizer. The quantized discrete time signal, okay, discrete sampled signal, converted into binary by using an encoder. Okay. So this one is the quantization of this one is the PCM transmitter simulator output. Okay, and the analog signal is generated by the black color. The quantizer signal is generated by this one, and the PCM encoder output we are going to see it in the Scilab console window. Here, number of levels L is equal to 16. So number of bits used to code the sample value is equal to n equal to 4. Madam, are you able to read these 2 points, madam? Number of levels equal to L equal to 16.
Yes, sir.
Okay. Number of bits used for encoding sample values n equal to 4. Right. Okay. So number of levels L equal to 16. Check number of levels here are equal to 16. 1, 2, 3, 4, 5, 6, 7, 8. Here 8. So 16 levels. Okay. Okay. Each sample value obtained from the 16 levels are encoded with 4 bits, n equal to 4 bits. So the encoder output we are going to the Scilab console window. We can go and check in the Scilab console window. So I here I haven't pasted all those things. So the construction protocol. So the Scilab console window appear and the encoder output. Okay, go to PCM pulse code modulation transmission. Number of levels equal to 16. Number of levels 16. Okay, and this one is the CTS signal, continuous time signal, and then uh, what you will get C. C is the what is C? C is nothing but your encoded binary binary PCM output. Binary PCM output. So what is uniform PCM? This function will perform what quantization, quantized discrete time signal. Okay, what is SQNR? This one is the uh, signal to noise ratio. Signal to noise ratio. Okay, what is this calling quantization program function quantization function, and what is this calling encoder encoding function encoding function encoding function. Okay, right. Execute this program, right? Okay. So quantization of sampled analog signal. Okay, number of levels equal to 60. Corresponding encoded output where we can go and check in the encoder here in the console window. So each sample value represented by four binary bits. Each sample value is represented by four binary bits. One, two, three, four. Why? Number of levels equal to 16. L equal to 16. 2 power 4 equal to 16. So number of bits is to encode sample value equal to 4. 2 power 4 equal to 16. That 4 is nothing but number of bits. Okay. What happened to number of levels equal to 8? Yeah. Number of levels equal to 8. So you should get 4 in the rising edge, 4 levels in the rising edge, 4 levels in the falling edge. With no echo. Yeah. 4 levels in the rising edge and 4 levels in the falling edge. So this one is the maximum value. What is the corresponding encoder output? What is the corresponding encoder output at this point? I come to the chat window. I'm posting the question here. For L equal to 8, L equal to 8, what is the maximum encoded value? Either 111 or 4 ones. For L equal to 8, what is the encoded maximum encoded value? Either 111 or 111. Madam, post this question in the YouTube.
Yeah, okay, sir.
Is it possible to get answer for this one? Okay. Um, for L equal to 8, what is the maximum encoder value? Either 111 or 1111. And the second question, um, the mean square error between original analog signal and reconstructed analog signal analog signal is maximum sorry is minimum in which case? Either L equal to 8 or L equal to 16 levels. In square between original analog signal and reconstructed analog signal is minimum in which case? Either L equal to 8 or L equal to 16 levels. Okay, so move to the next PPT, next slide. Delta modulation. Delta modulation. Um, delta modulation. This one is the block diagram of delta DM delta modulator of delta modulation DM transmitter. Okay, so this one is the data line shows the an accumulator. Okay, the accumulator is generates a approximate previous input. So what actually you are feeding the input to the quantizer, error between the um, previous what error between the present input and approximated present input. You are feeding the error. Actual, you are not actually feeding the sampled signal. You are feeding the error between these two to the one-bit quantizer. We are getting output B and T of S. What is B and T of S? How many number of bits you are getting at the delta modulator output? Only one bit only. So what is in other words, delta modulator is called as a one bit PCM. PCM, a simple ordinary PCM is an n-bit PCM. You are getting n-bit output, n number of bits output. In delta modulator, you are getting one bit output. Since you are feeding the error between these two inputs, that the error is quantized and encoded, you will get only one bit at the delta modulator output. Only one bit at the delta modulator output. Here, so this one is simulator of the delta modulator. Actual analog signals denoted by the black color sine waveform, and the accumulator integrator output is denoted by the x cap of NTS. This one, S cap of NTS is denoted by the red color integrator output. The difference between these two, that is the error E and T of S, is denoted by the blue color, green color error signal, and the delta modulator of B and T of S is denoted by the blue color like waveforms. Here you are getting positive peak, that is one binary one values up to this point. Why? Because the sine wave analog input is greater than the integrator output, so you will get binary ones at the delta modulator output. From this point to this point, again some fluctuations. Sometimes sine waveform greater than the integrator output, sometimes integrator output greater than input x of nt. So you will get ones and zeros here. From this point to this point, from um, this point to this point, the integrator output is greater than the original input sine waveform. So you will get binary zero at the delta modulator output up to this point. Okay, from this point, the sine waveform, sine wave input is greater than the integrator output. So you will get again binary one here. So the green color is the error between this sine wave and integrator output. Green color. Okay. Go to delta modulation. Open delta modulator. Enter the amplitude of the signal. Okay. Go execute this program. Close this previous figure window. Close this previous figure window. What is the value of amplitude? You can give any value. 5. Okay. This was the delta modulator output. Okay. The error is maximum in the slope. Check the green color error is very high in the slope. In the slope layer, sine waveform on the slope layer, you are getting very high error. Here also. Here also in the slope, you are getting very high error in delta modulation. Okay. How much you are getting mean square error? 1.19. 1.19. 1.19. How much you are getting mean square error? That is a error between the original input sine waveform x and the integrator output x cap of nt. Mean square error is equal to 1.19 in the case of delta modulator. In the case of delta modulation. In the case of delta modulation. Okay. Go to this figure. We are going for some other modulator, adaptive delta modulator. Why we are going for adaptive delta modulator? The slopes of the analog signal, you are getting very high error. What are those errors? Slope overload distortion or slope overload noise. Okay, and also in the case of peak point, flat point of analog signal, you are getting some other noise called as granular noise or hunting noise. In the slope, you are getting slope overload distortion noise. In the flat point of analog signal, you are getting the hunting noise or granular noise. These are the two main errors occur in the ordinary delta modulator. That's why we are going for adaptive delta modulator. What is adaptive delta modulator? Adaptive delta modulator changes its step size according to the slope of the input analog signal. Okay. What is adaptive delta modulator? This one is the block diagram of adaptive delta modulator. Okay. So what changes you have made in the delta modulator? You are using the logic for step size control. An additional block in the delta modulator called as logic for step size control. Okay. You are going to implement this block in the software along with the delta modulator program. You have already delta modulator program. What you are going to insert in the adaptive delta modulator program, you have to add additionally this block logic for step size control. Okay, you have to write a program. You have to insert few program lines, Scilab code lines, so that you can change the delta modulator into adaptive delta modulator. Okay, go to Scilab console, open adaptive delta modulation, adaptive delta modulator, adaptive delta modulator. Okay, so this was the logic. Here I have used. You can write your own logic, right? Anyway, see here this was the logic. Checking the slope of the input signal. According to the slope of the signal, I'm going to change the step size of the adaptive delta modulator output. Okay, you can write your own logic so that you can reduce the difference between the original discrete time signal, analog signal, and the synthesized analog signal. Okay, so that you can reduce the difference between xn of t and x cap of nt. You have to write the logic so as to reduce the difference between the xn of n of t and the integrator output s cap of nt. Okay. And here also we are going to check what is the mean square error for this case. Give the same value 5. Okay. Here the error is reduced almost uh, more or less you have the same value. So this blue color is the x n of t, This red color is the integrator output, feedback accumulated input or integrator output. This red color, this one. So here the error between the analog signal and feedback accumulator input, that is the integrator output, is reduced here. Here also the error is reduced. Okay, this one is the adaptive delta modulator output, and check what is the value of mean square error. You can compare the mean square error. So you will get a very low error compared to the delta modulator. This one work in this PowerPoint presentation. So this one is the delta modulator output. So you are getting the very high difference between the original analog signal and the accumulator input, that is integrator output. Here also you are getting a very high error, high difference between the original sine waveform and integrator output. Go to this, right? The feedback accumulated input, that is the integrator output, overlap with the analog signal. So you can write your own logic. What is the logic? You have to import those logic here, right? Go to line coding. So what is line coding? They are having different line coding techniques. In this FTP, we are going to see 4 different line coding techniques: unipolar format, NRZ non-return to 0 polar format, non-return to 0 bipolar format, Manchester format. In unipolar format, symbol 1 is, that is the binary 1, is represented by transmitting a pulse. Symbol 0 is represented by switching of the pulse. In NRZ polar format, a positive pulse is transmitted for symbol 1, a negative pulse is transmitted for symbol 0. In NRZ bipolar format, positive and negative pulses are used alternatively for transmission of 1 and no pulse for transmission of zeros. In Manchester format, symbol 1 is represented by transmitting a positive pulse for one half of the symbol duration and negative half for remaining half. For symbol 0, these two are appear in reverse. That is, negative pulse for one half, first negative pulse transmitted for one half of the symbol, and then followed by positive pulse for one half of the symbol. This one is a simulator output, unipolar signal, no pulse is transmitted for binary 0. Okay, for binary 1 transmitted with positive pulse. Okay, in polar 4, binary 0 transmitted with -1, binary 1 is transmitted with +1. In bipolar format, alternative binary ones, this one and this one, both are binary ones. The first binary one transmitted with a positive value, followed by a second binary one transmitted with a negative value. Binary 0 are transmitted with a 0 value. This one is the Manchester coding technique. Manchester coding technique. So the first binary one and the binary one, first half transmitted with a 0 positive value, and the second half transmitted with a negative value. Binary 0, this one is binary 0. First half transmitted with a negative value, second half of the symbol transmitted with a positive value. Okay, go to line coding technique. Line coding technique. Okay. Madam, any answers for this one, madam? Madam? Madam?
Yes, sir.
Any answers for LE48? And what is the maximum encoded value? Either 111 or 4 ones. Mean square error between original analog signal and requested analog signal is confirmed in which case, either L equal to 8 or L equal to 16 levels. I have asked these 2 questions. Any answers for these 2 questions, madam?
Yes, sir. Arun Kumar sir from Kadalur has been answered this. For the maximum encoded value, it is 4 1, sir. And then for L is equal to, that is a mean square error for the value of level is L is equal to 16, sir.
The mean square error between original analog signal and reconstructed analog signal is minimum for L equal to 16. Okay,
Yes, sir.
madam. Correct. That because we are using a more number of binary digits to represent a sample value, so you can get you can get reduced noise power. So signal to noise ratio automatically increase. Okay. For first question for L equal to 8, what is the maximum encoded value? 111, 3 ones. Number of levels 8. We are going to use 3 bits only. So maximum value equal to 111, 3 ones only, not 4 ones. Okay, ma'am.
Okay, sir.
And then for delta modulator and ADM, uh, it is having granular noise and slope overload, slope overload noise, slope overload noise. It's having granular noise and slope overload noise. If we second question, if we increase amplitude of the um, delta modulator input analog signal, what happened? What happened to the mean square error? Either increase or decrease. Having granular noise and slow pole noise. To increase the amplitude of the DM input analog signal, what happened to the MSC mean square error? Either increase or decrease. Okay, madam. Now we are going to post these questions in the YouTube, madam. Get the answers. Okay, madam. Okay, madam. And now we are going for line coding technique. Okay. For unipolar, binary 0 is transmitted with a 0 value. Binary 1 is transmitted with a positive value. For polar, binary 0 is transmitted with a negative value. Binary 1 is transmitted with a what positive value. Okay. Okay. So this one is binary 0. This one is 1, 1, 0, 1, 1, 1, 1, 1, 1. Okay. Right. Mm, 8. Okay. So this one is binary 0. Madam, are you able to read this, madam?
Yes, sir.
This one is binary 0 and this one is binary 1. This one is binary one, and this one is binary zero, and this one is binary one, binary one, binary one, binary one, binary one. Sorry, this one is binary zero, three zero, 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 one, and one. Okay, so this one is zero, one, one, zero, one, zero, 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 one, one, zero, one, one, zero, one, zero, 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 zero. So the previous one transmitted the positive pulse, and the next one is transmitted with the uh, negative pulse, and then the next one transmitted with the positive pulse. So zero in ancestor coding, first transmitted with the first half transmitted with the negative value, and second half transmitted with the positive value. Binary ones, binary ones. First half transmitted with the positive value, and the second half transmitted with the negative value. Negative value. Okay. Okay. The channel equalizer. Channel equalizer is a very important concept in the case of wireless communication. And in the third chapter of wireless communication, usually you have a channel equalizer. Okay, in the channel equalizer, main important filter you are going to discuss in channel equalizer is an LMS adaptive filter. Adaptive filter, simply adaptive filter. So, what is an adaptive filter? Adaptive filter usually we prefer FAR filter, whose filter coefficients are uh, changing in accordance with the um, input and feedback. Input and feedback. So, what is an adaptive filter? Adaptive filter is an FAR filter. Initially, the adaptive filter coefficients are initialized to zero value 1. The adaptive filter coefficients are updated according to the value of um, xn of t in this figure and en of t. Xn of t and en of t. Okay. So, what is the application of this adaptive filter? The adaptive filter may be used in the case of channel equalization purpose in wireless communication, in telephony and speech processing and music. We are going to use this adaptive filter for echo cancellation or noise cancellation. The same adaptive filter may be used in the image and video processing, where we are going to use the 2D FAR filter. 2D FAR filter. In speech processing, channel equalization, simple channel equalization, echo cancellation, and all, we are going to use 1D FAR filter. For image and video processing, we are going to use 2D FAR filter. 2D FAR filter. So, adaptive filter is an FAR filter whose filter coefficients are initially initialized to zero value, and then the filter coefficients are updated regularly according to the input value and the error value fed back to the adaptive filter. So, what are the applications of adaptive filter? Adaptive filter is for act as a channel equalizer in the case of wireless communication. Okay, and speech or telephone, etc. Where we are going to use this one for noise cancellation, echo cancellation, okay. And image and video processing, we are going to use the suppress unwanted noise, okay, okay, etc. So how I am going to demonstrate adaptive filter here for you for this FTP. Here I have a, I don't have any channel, so I'm going to give or one sinusoidal input to the adaptive filter, and then instead of error, I'm going to add some instead of some channel impulse response, I'm going to add some random noise, okay. And what is another input? The signal plus noise to the adaptive filter. So the adaptive filter coefficients are updated regularly according to the algorithm called as least mean square algorithm, LMS algorithm. After some iterations, some 100 or 200 iterations, I will get this at the adaptive filter output, this signal at the adaptive filter output. Noise suppressive signal. This was the original sinusoidal signal, random noise. I have generated the random noise instead of channel impulse response something. I just added this random noise with the original analog signal. So this was the signal plus noise. I'm feeding the signal plus noise and the error to the adaptive filter. After some iterations, 100 or 100, 200 iterations, I will get this output at the adaptive filter output. So for adaptive filter, there I am going to how I am going to demonstrate adaptive filter here. Instead of x of np, I am going to give the signal with some noise, okay, and the error signal as usual, and the I'm going to remove the noise present in the signal. So here this adaptive filter for my application, I am using this adaptive filter as a noise canceller. Noise canceller. Noise present in the sinusoidal signal. Noise canceller. Okay. Go to this one. There is adaptive filter. LMS adaptive filter. LMS adaptive filter. Execute the program. So this one is the original signal. This one is the original signal. Madam, both program and figure ரெண்டுமே clear தெரியுதா மேடம்?
Yes, sir. Both program and the figure is visible.
Okay, okay. Here I am using this adaptive filter as a noise canceller. Adaptive filter may be used for different applications. Channel equalization, noise canceller, echo canceller, etc. So many applications we can use adaptive filter. Okay. Here I am going to use this adaptive filter as a noise canceller to cancel the to suppress the noise present in the sinusoidal signal. So what is this signal? This original signal. This original signal is nothing but this X. Original signal. Okay, this X. And then what is this random noise? This one was the random noise. Random noise generated with the built-in function present in the Scilab. And then what's that one? Signal plus noise. This one is signal plus noise. Signal plus noise. Okay. What is zeros order comma 1? FER filter filter FER filter, no, adaptive filter. Adaptive filter, adaptive filter coefficients are initialized with 0. Initialized with 0 value. Okay. What is mu? Signal power. Signal average power. Average power. What is this one? LMS algorithm. How to update adaptive filter. To update adaptive filter coefficients. What is this one? A photo 1 2010 home of refreshes. இங்கே update பண்றோம். இங்க வந்து adaptive filter coefficients are updated here. Okay. First I'm going to plot the input signal. First row, first column. Second row, first column, noise. Third row, first column, noise signal plus noise. Fourth row, first column, noise remote signal. Which one is noise remote signal? Where it is desired? Noise remote signal. Noise remote signal. Okay. So original input signal, random noise signal plus noise, noise remote signal, noise remote signal. Okay, noise remote signal. Okay. Okay. And then we shall go for okay. Yeah, everyone is having mobile phone or laptop in your hand. So go to Google Colab. Right? In Google Colab, we are going to run the Python program. Madam, is there cancel on this, madam? DM and
Yes, sir.
ADM, which is having
Yes, sir.
granular line, slope overload noise. என்ன ஆன்சர் மேடம் வந்து மேடம்
DM is having both, sir.
DM having both
Analog
ADM வந்து
and slope overload noise.
Okay, ma'am. If you increase amplitude of the DM input analog signal, what happens to the MSC mean square and either
Increases.
increases because if you increase the amplitude of the analog signal in the DM, if you increase the amplitude in the sense you are going to increase the slope of the input analog signal. If you increase the slope means you will get more error at the DM, more error between the original signal and the integrated output. So if you increase the amplitude in the sense, you are going to increase the slope of the input signal feeding to the delta modulator. So automatically the difference between the original signal and the integrated output will increase. It will increase the error. Difference between the original signal and the integrated output. Okay. So mean square error automatically increases. Okay. Madam, if you want to simulate more programs in Scilab, go to um, um, Scilab.org, atoms.scilab.org. Madam, are you able to view this, madam? The open பண்ணிக்கிற page தெரியுதா madam?
Yes, sir. It's visible, sir. Skylabs.
Atoms.scilab.org. Different users have created different toolboxes for different applications. Go to technical. Here I have developed analog and digital communication toolbox. You can download the toolbox. This one will work both in Windows and Linux, invariant of Scilab versions, because I have used simple Scilab coding. What I did, I don't have used any what built-in functions available in Scilab. So those programs are suitable for any Scilab version. You can download this one from atoms.scilab.org and go to scilab.in. Scilab.org is developed by the French community, French scientist group. It's an international website. And go to scilab.in. So already, madam, send you all those things 2 days before. Go to scilab.in. Okay. Go to textbook companion project. Scilab.in developed by the IIT Bombay. Completed books. These links are already sent by madam 2 days before. You can check your email ID. Okay. Go to electrical and engineering and electronics engineering. Select uh, digital communication. And go to digital communication by Simon Akian. The entire book is coded by me, Scilab coded by me. Right? Download PDF or download codes. Okay. The entire Simon Akian book coded by me, so you can refer those programs. Or you can individual codes, run those codes in your program, or run those codes in your Scilab. Okay. Okay. And where you can download Scilab, go to scilab.org, scilab.org, go to download, Windows version. Madam, are you able to see all those things, madam? Different websites,
Yes, sir. Yes, sir.
scilab.org. Okay, download Scilab from scilab.org. Okay, if you want to work in Scilab cloud, you can work here. A equal to 2, some B is equal to 3. No need to install Scilab. C is equal to 2 plus 3. Sorry, A plus B, A plus B, print C. Sorry, display C. Display C. Execute this one. A equal to 2, B equal to 3, C is equal to 5. Suppose if you want to work if, in your mobile phone, from your mobile phone, you can use Scilab Cloud, cloud.scilab.in. Okay. The links எல்லாமே already sent to your madam, so you can get it from your madam. Madam already sent to you check your mail. Okay, மேடம், இப்போ நம்ம இது சைலாப்ல ஒரு ஒரு 10 எஸ்டிமேட் கிட்ட பார்த்துருக்கோம்.
So all the materials have been shared to the participants, sir.
ஓகே மேடம். இப்போ பைத்தான்ல வந்து ஒரு 4 எஸ்டிமேட் பார்த்துக்கலாம் மேடம். பைத்தான்ல ஒரு 4 எஸ்டிமேட் பார்த்துக்கலாம், முடிச்சிடலாம். அதோட ஒரு 10
Okay,
நிமிஷம்
sir.
தான். ஓகே
Okay, sir.
ஓகே. So go to type Google, right? Google Colab. This one you can what open from your mobile phone itself. No need to install Python libraries in your laptop, or if you can use Google Colab in order to do all Python related projects. I already um, done one program for this FTP stored in my Google Drive, ADC JPR FTP .ipython. That is visible, madam. ADC underscore JPR underscore FTP .ipython.
Yes, sir.
Yeah. The program already sent to you in the drive. My Google Drive link already sent to you. You can download Scilab programs, Python programs, and this PowerPoint presentation also. Open this. Okay. Okay. Here I have done 7 experiments related to ADC using equals command. 7 experiments using ADC. Tomorrow morning, just cross check my program. This one is for AM modulation. Run the code by pressing this button. So since the program is recorded in YouTube, so if you are not able to follow, you can download this video from the YouTube. Okay, you can start to practice. Since the program is streamlined in YouTube, tomorrow morning you will get this YouTube video. You can download that video. You can play that video. You can run this program. If you have any doubt, send me a mail. The mail ID already sent to madam. Okay, so madam having my mail ID and also on my WhatsApp number. Okay, enter the analog and digital communication program you want to run. So what program do you want to run? You I equal to 0 amplitude modulation, I equal to 1 frequency modulation, I equal to 2 phase modulation, I equal to 3 amplitude shifting modulation, I equal to 4 frequency shifting modulation, I equal to 5 phase shifting modulation technique, I is equal to 6 direct sequence respective modulation technique. So go and check whether this program will work or not. 6. Press enter. Yeah. This one is the direct sequence respective modulation technique. Okay. Okay. First one is data. Second is spreading code. Third one is the carrier signal. and the fourth one is the product signal, and the fifth one is the system. Okay, if you want to show some space, you can give some space. So figure கொஞ்சம் நீட்டாக இருக்குன்னா கொஞ்சம் ஸ்பேஸ் கொடுத்துக்கலாம் நீங்கள் ப்ரோக்ராமில் கொஞ்சம் ஸ்பேஸ் கொடுத்துக்கலாம். Suppose if you want to run the fifth program, space heating molecule, space shifting modulation technique. Enter the carry signal frequency in hertz, some 2 hertz. Sampling frequency in samples, say some 10 hertz. Carrier amplitude in volts, some 5 volts. Split data to be modulated. Um, 1 0 1 0 1 comma 0 comma 1 comma 0. Okay, so this one is the phase modulated BPSK output. Phase modulated output. You can save this image. Save image as PNG image, by default PNG image. Desktop, download PNG. Open foreign folder. Open with main. Yeah. Okay. If you want a more clear picture, you can give some space or different plots. You can use different plots. Okay, different plots. You can use different plots. In a single plot, I have used all these three figures. That's why I'm getting this one. Some figure is some congested like. Okay. So if you want to plot in a separate figure, you will get the clear pictures. Clear pictures. Clear pictures. Okay. You can, if you want to download this program, by default it will save automatically in your drive. No need to save separately. If you want to download this program in IPython network format, you can download. Or if you want to download this program in .py format, you can download it. If you want to save, print this program, print and save it in PDF file format. Save as some PDF file format. Madam, anything related to Google Colab, madam? Madam, anything related to Google Colab, madam? This programming. Even you can download Python and install in your desktop PC or Python app in your mobile phone. But
Okay,
you
sir.
have to install these two libraries. Matplotlib, NumPy, you have to install separately in your Python. You can install Python, standalone Python in your mobile phone or laptop or desktop PC, but you want to install separately these two libraries, Matplotlib Python library and NumPy Python library. So what is the advantage of using Google Colab? No need to install all those Python libraries. By default, Google has all those Python libraries built in. So no need to install. Just start to type directly this program. No need to install those libraries in Google. That's the main advantage of using Google Colab. You can use even Python, standalone Python. Standalone Python. Go to file, recent files. நீ காலையில் ஓப்பன் பண்ணி ரன் பண்ணி பார்த்தேன். This one. Run this program. மேடம் இந்த விண்டோவில் இருக்க லெட்டர்ஸ்லாம் படிக்க முடியுதா மேடம்? ஆர் யூ ஏபிள் டு ரீட்?
Yes, sir.
Python. Okay. Enter the analog and digital communication program you want to run. Program number 6, I equal to 6, that's the 7th program. Okay. Here you are getting some clear pictures. So if you want to more clear, you can plot binary data, separate figure, spreading code, separate figure, carrier signal in separate figure, product signal in separate figure, and BPSK modulated output in separate figure. You can save this one, figure 1.png. And any doubt in using Google Colab, madam, and Scilab?
No, sir, it's clear.
Okay, madam. So in the PPT, related to my work, you can refer this website. Open source software Scilab can be downloaded. Python can be downloaded from this website. You can refer this YouTube video related to Google Collaboratory for Python usage, and you can refer my Scilab coded Python Scilab coded Simon Hackenbook using this link, and you can refer the Anna University Communications Lab Python coding in this link, and you can refer my Scilab atom, another digital communication atom, by the Scilab.org website using this link, and these are the references. Since this FTP is particularly for wireless communication, so both ECE and AAA commonly conducting this FTP. For ECE, you are using smart grid system. It's for AAA mainly focused on power and smart grid, and ECE mainly focused on wireless communication system. Just I am taking the basics in analog and digital communication. Those are not sufficient for you for wireless communication. Those things can give you some fundamental idea how to write Scilab code for analog and digital communication. But those programs are not sufficient for wireless communication. So for wireless communication, the textbook combining projects are available in the following links. You can refer these links. Madam, the references are clear. Madam.
Yes, sir, references are clear. Yes, sir.
Okay, you can download those codes from those links. Electronic Communication System by Kennedy and Davis. Scilab code available in this link. Electronic Communication Systems Fundamentals to Advanced Diplomacy. Scilab codes are available in this link. Analog and Digital Communications by S. Sharma. Scilab codes are available in this link. Digital Communication by Samanak and my book codes are available in this link. Propagation Engineering Wireless Communication, Abdullah Ghasami and Scilab code available in this link. Wireless Communication Principles and Practices, DS Rapport, Scilab code link available in this link. And then Wireless Communication and Networking, COS, Principle of Communication System, Top and Selling. Wireless Communication TL Single, Analog and Digital Communication Hutu, is available in this Scilab code link. And refer more textbook company projects in this link, and lab migration projects in this link. Okay, and these are my videos related to Python. Okay, Python. So this the last one, YouTube videos are related to my videos related to Python.
Application software developed by Institute of Road and Transport Technology. Institute of Road and Transport Technology is coming under Tamil Nadu government, and it is done by Tamil Nadu State for Transport Technology. Road and Transport Technology developed three applications: digital signal processing, digital image processing, and analog and digital application. These three applications are stored in this folder. Software applications developed desktop, CD, desktop. DSV.exe. The corporate figure will open. Close this figure. This corporate logo contains the author of the software, Dr. R. Sundar Kumar, and IRDT logo, Institute of Road and Transport Technology. Close this logo. Right. Enter the DSV programs want to run. Here I want to run an FIR high pass filter frequency response. The program number corresponds to FIR high pass frequency 500. Choose the sampling frequency, say some 2000. Right. You are getting the
So you can write your own applications in Python. Scilab is very difficult to create an exe file in Scilab, but in Python you can create a exe file for wireless communication. You can develop, you can write all those codes and put it in a single Python file and convert that Python file into exe application software. So that software you can use it for your laboratory purpose. So the last YouTube video you have seen is the software applications developed by me for digital image processing, digital signal processing, analog and digital communication using Python. Scilab, you can write the Scilab programs. Similar to the Scilab programs, is a free open source, but it's a difficult task to convert Scilab into exe file. But Python is very easy. If you are developing any, if you want to develop any applications for any engineering subjects, you can use Python. Scilab also better tool. It's a free tool, open source tool, particularly for electronics and communication engineering and EEE department. More suitable software for Scilab, more suitable software for electronics and communication engineering and EEE department. Because Scilab has more toolboxes related to communication, signal processing, image processing, video processing, and power electronics, power system analysis, control system. But if you want to convert into exe file, it's very difficult in Scilab. But it is much easier in Python. By using Python, you can develop your own application software. That is the .exe file. .exe file. By clicking the .exe file, you can install those software in your system, and you can use as a standalone software wireless communication. So any application, if you want to develop for any engineering subject, you can use Python. But Scilab has so many toolboxes. Madam, 5 more minutes, madam.
Yeah, okay, sir.
Okay. Okay. So why I am saying Scilab is um, more suitable for EEE and ECE. Here you are having sibling blocks also for Scilab for EEE and ECE. Signal processing, um, control system, right? So you are having sibling blocks for like MATLAB sibling. This XCOS is provided by the Scilab, similar to the MATLAB Simulink. Okay, so particularly for EC and EEE, this one is Scilab is a best software, and also Scilab provides so many toolboxes. If you want to install toolboxes developed by some others, you can go for Atoms. This was the Atom box, right? Go to signal processing. I mean, Scilab communication toolbox, serial communication. Go for uh, artificial neural network and Scilab communication toolbox, serial communication, and MATLAB to octave conversion. Okay. Data analysis. Bioinformatics. Education. GUI. And so many real time Scilab development, Windows tools, XCOS, similar to the Simulink. You can install so many toolboxes developed by some others. Okay. So what are the points I discussed here? I'm going to consolidate here. First one, simple simple analog and digital communication simulations. Okay, and then um, uh, how to use Scilab for wireless communication. What are the materials available for wireless communication using Scilab? Those things are discussed. And how to use Python for analog and digital communication, how to write Python code, how to simulate analog and digital communication experiments using Python, using Google Code and also standalone Python, and what are the merits available in the Scilab. Scilab, by using Scilab, you can do all the simulation experiments you already doing with MATLAB, right? MATLABல என்னென்ன எக்ஸ்பெரிமெண்ட் நீங்க பண்றீங்களோ ட்ரிபிள் டிபார்ட்மெண்ட் இசி டிபார்ட்மெண்ட் எல்லாமே Scilabல பண்ணலாம். ஓகே, Scilabல வேற டூல் பாக்ஸ் வேணும்னா அதையும் நீங்க டவுன்லோட் பண்ணிக்கலாம் பை யூசிங் Atoms. சப்போஸ் யூ ஆர் ஹேவிங் சம் MATLAB ஃபங்க்ஷன்ஸ், சின்ன ஃபங்க்ஷன்ஸ் இருக்கு, அந்த MATLAB ஃபங்க்ஷன்ஸை எப்படி Scilab ஃபங்க்ஷனாக கன்வெர்ட் பண்ணுறது பை யூசிங் MATLAB டு Scilab கன்வர்ஷன் டூல். MATLAB to Scilab conversion tool யூஸ் பண்ணி MATLAB ஃபங்க்ஷனை Scilab ஃபங்க்ஷனாக கன்வெர்ட் பண்ணிக்கலாம், Scilab ஃபங்க்ஷனை C ஃபங்க்ஷனாக கன்வெர்ட் பண்ணிக்கலாம். ஓகே ஓகே, இது வந்து Scilabோட அட்வான்டேஜ். பைத்தானோட அட்வான்டேஜ் என்னது? பைத்தான் வந்து இந்த மாதிரி ட்ரிபிள் டிபார்ட்மெண்ட் இசி டிபார்ட்மெண்ட் ஸ்பெசிஃபிக்காக அதிகமாக எதுவும் டெவலப் பண்ண வைக்கல, நாம தான் டெவலப் பண்ணிக்கணும். ஆல்ரெடி அவைலபிளாக இல்லை, ஒவ்வொருத்தரும் ஒரு லேபுக்கு கன்வெர்ட் பண்ணி வச்சுருக்காங்க பைத்தானில், பட் அதில் நெட்டில் அது அவைலபிளாக இல்லை. பட் யூ ஹவ் டு ரைட் அவர் ஓன் கோட் ஃபார் பைத்தான். பட் பைத்தான் யூஸ் பண்ணி நீங்கள் அப்ளிகேஷன் சாஃப்ட்வேர் டெவலப் பண்ணணும். அப்ளிகேஷன் சாஃப்ட்வேர்னா என்னது? நீங்கள் MATLAB சாஃப்ட்வேர் வாங்குறீங்க, உங்கள் சிஸ்டத்தில் போடுறீங்க, காப்பி பண்ணுறீங்க, இஎக்ஸி ஃபைலாக காப்பி ஆகும். அந்த இஎக்ஸி அப்ளிகேஷனை டபுள் கிளிக் பண்ணால் மேட்லாப் சாஃப்ட்வேர் உங்கள் சிஸ்டத்தில் இன்ஸ்டால் ஆகும். அந்த அப்ளிகேஷன் சாஃப்ட்வேர் வந்து பைத்தான் யூஸ் பண்ணி டெவலப் பண்ணலாம். ரொம்ப சிம்பிள், ஈஸியாக டெவலப் பண்ணலாம். இமேஜ் ப்ராசஸிங், வீடியோ ப்ராசஸிங், ஸ்பீச் ப்ராசஸிங், என்ன அப்ளிகேஷன் வேணாலும் பைத்தான் யூஸ் பண்ணி ஈஸியாக டெவலப் பண்ண முடியும். அது பைத்தானோட அட்வான்டேஜ். ஓகே, இப்போ கம் டு தி பாயிண்ட். இப்போ உங்களுக்கு வேற என்னென்ன டவுட் இருக்குது மேடம்? மேடம்,
Yes, sir. Yes, sir.
உங்களுக்கு என்னென்ன டவுட் மனதில் இருக்கு?
Sir, if participants have been asked any doubts, I will share with you, sir, through the mail.
ஓகே
Okay, sir.
ஓகே ஓகே மேடம், ஓகே மேடம். மேடம், இப்போ இந்த பாயிண்ட்ஸ் நான் சொன்ன பாயிண்ட்ஸ் கிளியர் கட்டாக புரிஞ்சுதா மேடம்?
Yes, sir. Yes, sir.
அதாவது வந்து by using Python you can develop any application software. It's better to use Google Collaboratory for Python. By using Scilab you can do all the experiments, analog, ECE and EEE experiments, okay, which are already you are doing using MATLAB. MATLAB யூஸ் பண்ணி என்ன எக்ஸ்பெரிமெண்ட் பண்ணுறீங்களோ ECE டிபார்ட்மெண்ட், EEE டிபார்ட்மெண்ட், அதை Scilab யூஸ் பண்ணி பண்ணலாம். அவ்வளோதான் மேடம். ஒயர்லெஸ் கம்யூனிகேஷன், இந்த FTP வந்து மெயினாக ஒயர்லெஸ் கம்யூனிகேஷன் ரிலேட்டடாக இருக்கிறதுனால அது சம்மந்தமாக நிறைய ரெஃபரன்சஸ் கொடுத்துருக்கேன். அந்த Scilab ப்ரோக்ராம்ஸும் அந்த புக்கும் ஃப்ரீயாக scilab.in வெப்சைட்டில் அவைலபிளாக இருக்குது. scilab.in வந்து ஐஐடி பாம்பே வந்து டெவலப் பண்ணது. அந்த இந்த லைசன்ஸ் சாஃப்ட்வேர் வந்து நம்ம யூஸ் பண்ணுறோம்னா நிறைய மணி ஸ்பெண்ட் பண்ணுறோம். அந்த லைசன்ஸ் சாஃப்ட்வேர் யூஸ் பண்ணுறோம்னா மணி ஸ்பெண்ட் பண்ணுறது அவாய்ட் பண்ணுறதுக்காக scilab.in வந்து மினிஸ்ட்ரி ஆஃப் ஹியூமன் ரிசோர்ஸ் அண்ட் டெவலப்மெண்ட் வந்து ஃபண்டு வாங்கி ஐஐடி பாம்பே வந்து டெவலப் பண்ணி அதில் இன்ஜினியரிங் சப்ஜெக்ட்ஸ் எல்லாத்தையுமே மோஸ்ட்லி மேத்தமெட்டிக்ஸ்லேருந்து மெக்கானிக்கல், ஏரோநாட்டிக்கல் இன்ஜினியரிங் எல்லா இன்ஜினியரிங் சப்ஜெக்ட்ஸும் Scilab-ல வந்து இந்த லைசன்ஸ் சாஃப்ட்வேர் கோட் பண்ணியிருக்காங்க இல்லையா, அது பதிலாக Scilab யூஸ் பண்ணி கோட் பண்ணி எல்லா புக்ஸும் அதில் போட்டிருக்காங்க. அந்த கோர்ஸும் ஃப்ரீயாக அவைலபிளாக இருக்கும், புக்கும் ஃப்ரீயஸாக அவைலபிளாக இருக்கும். அதை நம்ம எஜுகேஷன் பர்பஸ்க்கு ஃப்ரீயாக யூஸ் பண்ணிக்கலாம், நம்ம லேபரேட்டரி பர்பஸ்க்கு ஃப்ரீயாக யூஸ் பண்ணிக்கலாம், தப்பு இல்லை. எந்த கமிட்டி விசிட் வந்தாலும் சரி, NACA இருந்தாலும் சரி, NBA இருந்தாலும் சரி, இல்லை அண்ணா யூனிவர்சிட்டி அப்ளிகேஷன் கமிட்டியாக இருந்தாலும் சரி, Scilab யூஸ் பண்ணிங்கன்னா இந்த சாஃப்ட்வேரை Scilab யூஸ் பண்ணி ரீப்ளேஸ் பண்ணிக்கிறேன்னு சொல்லி காமிச்சிங்கன்னா அவங்க அக்செப்ட் பண்ணிக்குவாங்க இமீடியட்டாக. MATLAB யூஸர் வந்து 5 லெசன்ஸ் கேட்டாங்கன்னா Scilab யூஸ் பண்ணி எல்லா சிஸ்டத்துலையும் நாங்கள் அந்த டிஎஸ்பி லேபு, கம்யூனிகேஷன்ஸ் லேப்லாம் நாங்கள் கண்டக்ட் பண்ணுறோம் அப்படின்னா ஓகே, நெட்வொர்க்கிங் லேப்லாம் கண்டக்ட் பண்ணுறோம்னா ஓகேன்றோம். உங்களுக்கு வந்து லைசன்ஸ் கேட்க மாட்டாங்க, MATLAB லைசன்ஸ் எல்லாம் கேட்க மாட்டாங்க. Python யூஸ் பண்ணாலும் ஓகே. ஓகே மேடம்?
Yes, sir.
Okay, madam. Thank you, madam. Thank you for giving me the opportunity to deliver
Thank you, sir.
lecture in your valuable institution. Thank
Yes,
you
sir.
for giving
Deepika,
me the opportunity.
kindly proceed, ma'am.
Yes, sir. Yes, ma'am. Thank you, sir. The session was really interesting and informative. Hope our participants would gain information from this session. Now I request Ms. Nancy, ma'am, to felicitate our chief guest with momentum. Please, ma'am.
On behalf of JPR Institute of Technology, we would like to share this momentum to you, sir. Kindly accept the momentum, sir.
Thank you, madam. Thank you, madam.
Thank you, sir. Really, the session is very informative and we have gained more knowledge about this coding everything, sir. Thank you.
Thank you, madam. Thank you.
Thank you all. It's my privilege to have been asked to propose a vote of thanks on this occasion. On behalf of JPR Institute of Technology and of my own behalf, extend a very hearty thanks to our director, Sir Dr. N.M. Murray Wilson, and our principal, Ma'am Dr. L.M. Murray Livingston, for providing encouragement and support to organize the event. I would like to thank our chief guest, Mr. Senthil Kumar, for enlightening us with their knowledge. Today's faculty development program was full of knowledge and information. I request the participant to fill the feedback form which is posted in the chat box to get e-certificates. At last, I would like to thank the entire crew of the event. Thank you all.
Yes, sir. We can wind it up now, sir. Thank you, sir.
Oh, okay, ma'am. Thank you.